Well, hello guys, Mr. G here with another lesson related to momentum for the grade 12. Have you ever wondered how is it possible that a very thin person who trains martial arts can break a lot of blocks or piece of wood, things like that? I always wanted to learn and break woods, but the trick behind, even though they know a lot of techniques, obvious, but the trick behind is a little bit of physics. They know a law, or maybe they apply a law without knowing. The same happened with the airbags. Will you wonder how does airbag help to save life, and why did they install airbags before? Previously there were no airbags in the car, or why is a seat belt? In the previous car, all cars, 50s, the 90s, 50s car, there were no airbags. And they eventually installed the airbag. Why did they change the strength of the car? Long time ago, on those 1950, 59, those cars were very hard, very strong, and they changed it now for something that is literally very soft car, and they can get matched very easy at the front. But there's physics behind that, and it's not just because they want to make cars easier. So all this one is going to be explained by a law we're going to learn today. This is called Newton's second law, or Newton's law in terms of momentum, not Newton's second law, Newton's law in terms of momentum. We're going to learn about it. Please watch the video, it's quite interesting, and I'll see you at the end of the video. It's Mr. G here, and we are going to be doing the third lesson related to momentum for the grade 12. This time we're going to be talking about Newton's law in terms of momentum. And previously we already spoke about Newton, so we know a little bit about Newton. We'll learn 3 Newton's law of motion, and then we'll learn about Newton's law of universal gravitation. To me personally, as I said before, Newton is the greatest scientist of all time, but there is many scientists that very good scientists, but to me it's the one that gave the most work. Okay, so in Newton previously, let's recall what we learned in previous grade about Newton's law of motion. So this is Newton's law of motion, and there we have 3 main laws. So Newton's first law Newton's first law, which is called law of inertia. Note, it is called law of inertia, but it's not inertia. Inertia is a property that all the object has. Now, Newton's first law is a law. Okay. Now, what this law states? This law states that an object continues in its state of rest of uniform motion. Uniform motion means at constant velocity. Constant velocity means same magnitude and same direction. Okay. Now, unless it is acted on by unbalanced net force. Now, how to use Newton's first law? What is the formula? Well, net force is going to be equal to 0. Remember, you can write net force, or you can write a resultant force, or you can write sum of the forces. Now means that the net force is equal to 0. If the net force is equal to 0, then the object is going to be moving with uniform motion, that means at constant velocity, or will stay at rest. That is Newton's first law. This lesson is not about Newton's first law or about Newton's law of motion, so we're not going to take long here. Now, Newton's second law. Now let's go to Newton's second law. Now, Newton second law of motion. These are the law of motion, and this is called law of force. Let's use the same color there. Law of force, Newton's second law. Now, this law, what does the Newton's second law state? They say that if a resultant force acts on an object, it will cause the object to accelerate in the direction of the resultant force. Now, important, the acceleration of that object will be directly proportional to the resultant force. That is the first very important part in this definition. And second is that that acceleration is inversely proportional to the mass of the object. And this is the mathematical equation for that formula. If we write that one in symbols, we have that acceleration is directly proportional to the net force or resultant force. Now, this happens if mass is constant for the same object. Mass constant, okay? And acceleration is inversely proportional to mass when the force is constant. So in this case, force must be constant or net force. If the net force is constant, then the acceleration is inversely proportional to mass. But remember, we're doing Newton's law in terms of momentum, no Newton's second law of motion. This is just a recall. And then the third Newton law of motion was the action-reaction. So that was Newton's third law. So Newton's third law, which is called action-reaction. And this law states that if object A exerts a force on object B, then object B exerts a force of equal magnitude on object A, but in opposite direction. And this is the formula for that one. So this is the three Newton's law you learned in previous grade. Newton's law, first Newton's law of inertia, Newton's second law or law of the force, and Newton's third law or action-reaction. Okay, now let's go to the one we are doing now. Now, to do that Newton's law in terms of momentum, the first thing we are going to use is recall Newton's second law for the second time. So we are going to start by writing down the formula of Newton's second law of motion. Okay, so we have that the net force is equal to the mass multiplied by the acceleration of the object. Okay, and before we carry on, let's also recall the definition for acceleration that we learned also in previous grade, that was learned in grade 10. So let's recall that acceleration is the rate of change of velocity, and this is term important. Now every rate is when you divide by time. That means rate. Rate, in other words, is not other thing than how fast something happens. So this is the rate, how fast velocity change. Now this is change in time. And remember, change in time means final minus initial. But most of the time, the initial time is 0, because there is when we start to study the motion. And then what is going to be on top is going to be the change in velocity. Is how fast velocity change. And this is what we call acceleration. So this is the definition for acceleration. How fast the velocity change. Okay? How fast velocity change. Rate of change of velocity. Remember, we learned in the previous lesson that change means final minus initial. So we can say that acceleration is equal to final velocity minus initial velocity divided by time. So this is the same as we said before, how fast this velocity change from initial to final. Okay, so this is acceleration. It's the same formula. Okay, now we may substitute this one in Newton's second law, and then we have that net force is equal to the product of mass multiplied by, I'm going to open bracket, final velocity minus initial velocity divided by time. Okay, this is what we have when we substitute the formula of acceleration in Newton's second law. And this is simple mathematics. If you multiply this m by the final velocity and the initial velocity, this is simple maths. You will have that net force is equal to mass multiplied by final velocity minus mass multiplied by initial velocity, everything divided by change in time. And my lovely children, my lovely people, this here is change in momentum. that we learned in the previous video. Please go back and watch it if you did not. Okay, so saying that, we can write now that F net is equal to, or net force is equal to, this here is what we call change in momentum. Please recall that one from last year. This one here is change in momentum. So then we can say this one is equal to change in momentum divided by change in time. And this, my people, is what we call Newton's second law in terms of momentum. And applying what we said about acceleration, we divided by time, so this is called rate, and this on top is change in momentum. So in other words, it's how fast momentum change. That is the Newton's second law. So Newton's law in terms of momentum said that the net resultant force, net or resultant force, is equal to the rate of change of momentum of the object. That is Newton's second law in terms of momentum. It's quite easy, and this is the analogy. Where is it coming from? Why is it called Newton's second law? Because it's a derivation of Newton's second law of motion. But now note the following. If you are doing an exam and they said define or state Newton's second law of motion, this is not Newton's second law of motion. Newton's second law of motion is this one we spoke about before. If they said, or if they ask you to define or state Newton's second law in terms of momentum, then this is the one they want you to answer and define. Now, let's analyze this formula just a little bit. First of all, you know, or you must know, that the net force will always have the same direction as the change in momentum if the time is constant, okay? Same direction. Remember, the force is the one that produces or causes that change in momentum. So this is an important thing that you must remember. The net force will have same direction as the change in momentum. And the other very, very important thing is that the net force is going to be inversely proportional to the time if the change in momentum is constant. Now, this one here is very, very important. It is used in our days. It's used all the time. This law is very, very important. Now, this explains the use of the seat belt in the car. Now, what this means here? It means that the smaller the times become, the bigger the force will be. So if you manage to reduce the time, then you will have a very big force there. This is happening with the martial arts people when they break blocks, for instance. What they do is they do it so fast, the time is very small, and therefore the force here will be very big. So apart from force and so on, they need to have, and they need to do it very, very fast, because the faster they do it, the bigger the force will be. Now, this happens also with airbags. For example, when you have an airbag in a car and the airbag inflated, you are increasing the contact time between the person and the car. If you increase the time, then the force will be smaller. Alright, so all the idea is to increase the time so the force is smaller, and therefore the injury will be less. Okay, the same happens with a seat belt. If you have a seat belt, then the seat belt increases the time of contact, or time in contact with the person, and therefore the force will decrease. The new cars have something called crumple zone. Now, the crumple zone is the front side of the car, which is quite soft. So in case of an accident, that crumple zone will increase the time in contact with the object, and therefore the force will be less, and obvious less probability of the person, of the driver, to get injured. The same happens if somebody jump from certain height. You have to flex the legs. Now, as you flexing the legs, you are increasing the time in contact with the floor. And as you increasing the time, the force becomes smaller and obvious less probability to get injured. So that is quite important. We'll talk about this one later on. Maybe we're going to do an experiment if it's possible for you to see it. And this is Newton's second law in terms of momentum. Now, as always, let's look at one example real fast. Okay, so let's look at this example. This example says a soccer ball of mass 0.5 kilograms. Let's mark here the data. Move with a velocity of 12 meters per second towards a soccer player. So now this one is the initial velocity. That is the initial velocity is moving towards a soccer player. Just before the soccer player kicks the ball. So the soccer player kicks the ball away from him. When the soccer player kicks the ball, it moves with velocity of 15 meters per second in the opposite direction. And this will be the final velocity. Calculate change in the ball's momentum, the force exerted on the ball if the contact time is 1,2 milliseconds, and C represent the change in momentum in a vector diagram. Very good, because last time we did only one. So here, more or less, we did some data, but let's follow in the steps that we always do. First of all, let's do a sketch of this situation so you can understand better. Okay, so the first thing we're going to do is to sketch the situation. We have a soccer player, a ball is coming towards him, the mass of the ball, so let's use here to write the data. The mass of the ball is 0.5 kilograms. 0.5 kilograms. We have that the initial velocity is equal to 12 meters per second towards the soccer player, and the final velocity is equal to 15 meters per second away. Let's write meters per second, let's not write away. And remember, we said before we carry on, this was done in previous video, please go back there. We said that we are going to select what direction is going to be positive. So we're going to write towards as positive. This is very important. I ask you to please do that always. Toward is going to be positive. So if we go back here now to the data, the 12 is going to be positive and the 15 is going to be negative because it's away. Okay, so this is mainly the data, and they're asking us to calculate the change in momentum first of all, and then they're asking you to calculate the force. Okay, and they give us the time. So let's first write here the other data we have, which is the time. I'm going to write it on this side here, is equal to 1,2 milliseconds. Now milliseconds means 1,000, so you have to divide by 1,000. Okay, so this one is divided by 1,000, which is the same as multiplying times 10 to the minus 3 seconds. This is just data. Okay, we didn't do anything else. Now the mass of the ball is the same. We're working with the mass, so it's only one mass, it's only one object. The mass didn't change. Okay, so now how to calculate the change in momentum. Remember, change in momentum is equal to mass of the object multiplied by the final velocity minus mass of the object multiplied by the initial velocity. Now, because the mass didn't change, we have that the change in momentum is equal to mass bracket final velocity minus initial velocity, and we have to be careful with the direction. Okay, so change in momentum is going to be equal to the mass is 0.5 bracket, final velocity is minus 15 because it's in the opposite direction, and we say toward is positive, minus initial is 12. Okay, so when you do this calculation, you will get that the change in momentum is going to be equal to 13 negative 13,5 kilograms meters per second. Now note and remember, this minus here means direction. So the answer could actually be there. That means that E is away because toward is positive. But to be safe, as we did before, let's write the final answer as change in momentum is equal to 13,5 kilograms meters per second away from the soccer player. I just going to write away. Okay, so this is A. Now for B is very simple. They ask you to calculate the net force. Now here is where we are going to apply Newton's second law of momentum. Newton's second law of momentum. Now Newton's second law of momentum says that net force is equal to the change in momentum divided by the change in time. We read as rate of change of momentum, and the change in momentum was calculated. So that part is already calculated. It's 13,5 divided by the time, which is 1,2 times 10 to the minus 3. Okay, and when you do that calculation, you have that, let's to move a little bit up there, we have that the net force is going to be equal to 11,250 Newton. Note the following. I substitute the final answer positively as it is here, and therefore the direction will be the same. But other way to do it is rather to substitute the minus as it's on top there, minus 13,15, and will give you minus. Okay, just to be safe. You can substitute this final answer, and remember this is direction is away. It's going to be away because the net force would have the same direction as the change in momentum. But the best way is to substitute the first answer you got here with the negative, and you will get the negative answer. Now that negative answer means that the net force is equal to 11,250 Newton away. Okay, and this is the work done here. Okay, now let's do the drawing, the free body, the vector diagram for this question. And now remember, as usual, we are going to remember that the change in momentum is equal to final momentum plus minus initial momentum. You don't have to write this one, guys. It's not important to write. I just want you to remember. Now, the initial momentum was going to be in this direction. That is initial momentum using a vector diagram. This is the vector representing the initial momentum, but we don't want the initial momentum. We want the minus initial momentum, and minus initial momentum must be the same vector but pointing in the opposite direction. So this here is minus initial momentum, and this one is the one we are going to use for the addition. Okay, so now what is final momentum? I tried trying to write that, but with the vector. The final momentum was away. This was the final momentum, slightly longer, slightly bigger. That is the final momentum. So we are going to add. We are going to add final momentum and minus initial momentum using the vector diagram head to tail. So if we have the final momentum, all we have to do is here at the head adding the minus initial momentum, which is this one here. This one is minus initial momentum, and then the change in momentum is going to be from the tail of the first one you draw to the head of the last one. This one here is the change in momentum. So guys, this one here is the diagram representing the relationship between initial momentum, final momentum, and change in momentum. As I said before, there are other ways to do it. You can use any way that that you find easier. Other tutors will show you other ways. I'm sure maybe you'll find them easier, but this is the best way I found. So this is related to Newton's second law in terms of momentum. We learn about we recall Newton's second law of motion, Newton's first law of motion, and Newton's third law of motion. And then we did analyze how to arrive to Newton's second law, Newton's law in terms of momentum. We saw one example, and very very important, we analyze this formula and how does net force being affected by the change in time. Okay, if possible, we'll do an experiment. I'll see you next time. Next time we are going to be doing some. Next video we're going to be doing just some questions related to what we've done up until now. Very short video, just to practice 1 or 2 questions, and then we're going to go to a law. Okay, but thank you for watching. I'll see you next time. Subscribe on the channel and write comments, thumb up if you like the video, and you can ask any question. Thank you for watching. Welcome back. So now you know why those martial arts masters can break many blocks, and is even though they know techniques, they have to do with how fast they bump towards the wood, or they hit the blocks. The same happened with the seat belts in the car. You can see now that when you have the seat belt, the contact time between the person and the car is longer, and then the force is going to be less. And the same happened with the crumble zone we spoke about at the beginning of the video, when we said that a long time ago or years back the cars didn't have crumble zone. They were hard, they were made of pure metal, and those cars were quite hard. Now they have crumble zone, they're very soft, and then as they come into, so they take longer because the time is increased up until they stop. Therefore the force obvious on the passenger or the driver is less. But thank you for watching. We'll be making an experiment very soon, so you can see this law, and I'll see you next time. Please subscribe. Thank you for watching. Subscribe, you can send message, you can ask questions, and I'll see you next time. Mr. G here.